DreamCoder AI, wake and sleep programmer learning. Learning to code by growing library, training neural search, and fantasizing about code. So today I was reading this paper, DreamCoder AI, and so I was just trying to learn more from a little bit different areas as well, so to have sort of bigger picture about machine learning. If you like these videos about getting the juice of the paper, I will go very quickly through it. You can subscribe. You can also subscribe by mail on the blog here over at the end. Okay, so why to learn coding? So neural networks are sort of missing the system to from thinking fast and slow, popularized in this in that. So humans can do regression as neural networks. They can learn to recognize pictures of cats and dogs, uh, but they can as well think algorithmically. So they can formalize a knowledge into pieces. They can formalize algorithms and store them, and then recover them and execute them. And they can as well learn efficiently from small amount of samples. So what would be interesting is to have some kind of marriage of symbolic and neural machine learning. And there was this great podcast or video with from Machine Learning Street Talk with François Cholet, Intelligence and Generalization, which they have more discussing this sort of topic. So how DreamCoder paper works. So DreamCoder uses learned library of functions, learned neural search on program space, and also learned generator. Two, but about that later. Two, given inputs and output examples, we can produce program a best solution. So what is this best program? So the best program is obviously based on experience, sort of based on the functions that are in the library. There's usually not as one single solution. There are usually multiple solutions. But from experience, you tend to know from small amount samples what is being you are being to ask to compute, right? And yes, so the program space is very large, so we cannot search all the possible programs that solve these examples. So the DreamCoder does this, that he learns only functions that only selects functions as a solution if they solve the problem and as well are very short. And how to do this on this very large space of programs? They use neurally guided search. So that's the marriage part. They marry through optimizing the search using neural networks. So they sort of model this program space using neural networks. They have to serialize for the neural network to learn anything in the program needs to be serialized. So for example, they use lambda calculus to convert this tree, the program tree into a simple linear text. And then when they do this, they can learn the neural network and sort of recognize given input. It sort of know what kind of programs could solve this. And then they execute those programs and find the solutions. So for example, what kind of programs it tries to solve? So for example, list processing. So it does sums of variable length lists of values of numbers. It can, for example, learn to double numbers. It can find out what is an even number, what is an odd number in a list. In text editing, it can, for example, abbreviate names, drop last couple characters, can learn to do regexes. It can learn to draw graphics. So it controls a pen, and then using simple functions, it can draw different vector graphics. All right. How exactly this DreamCoder learns? So it has two major phases. It has wake phase and sleep phase. And sleep phase is made up of abstract and dream. So the program starts, the training starts with having primitives, which it can compose programs from. and then it loops over these two major phases. So the first wake phase, when the sort of program is awake, so it's awake and trying to solve programs it's given. It's usually in this paper it was given about hundreds of examples. It tries to solve them. If it solves them, it solves the solution into the memory. Then it transitions into the sleep phase, where first part of the sleep phase is to abstract. So it replaces successful solutions, and it tries to compress them by adding some new functions into the library. And then there is a second sleep phase. It's called dream phase, where because it needs to be sample efficient, it also uses some sort of simple generator, and it also replaces programs that it encounters, and it trains the search, right? So to find, during the wake phase, it uses this search to find solutions, but this search needs to be learned, and it's learned in the dream phase. It's in the dream phase by using a generator and replaying programs. So again, we have this wake phase, search for best solutions using the library, store the solutions, couple of solutions, top 5. And sleep phase, it tries to abstract, so it tries to add something to the library that compresses the programs it found. And then uses dream phase, where it replaces and generates new programs to train the search function, which is then used in the wake phase. All right, again, a little bit more into the wake phase. So it has neural network, which it's sort of this neural guided search is used there, and it's used a little bit. You can see it as an analogy to the AlphaZero. That AlphaZero also performs, when it plays chess. It does not only does self-play, which is a little bit like this dream phase, but it also does this neurally guided search, because the search space of possible positions in chess are too large. It sort of uses an intuition about the search space, which is learned into this neural network, and it makes a more efficient search and sort of more abstractive, more interpretive, if the neural network of course works. So the neural network Q ranks the potential solutions. So given input outputs, it returns programs probability. So it is sort of a distribution over programs given inputs outputs. They call it recognition model. And from those, it searches the best solutions. So the best solutions are the smallest, and which also solve the problem. And so it ranks the potential solutions given input outputs, and then it selects the smallest programs that solve this. It uses about 5 from those, and then store the solutions. In the abstraction phase, it proposes new library functions, and it again it tries to it has the solutions. It tries to compress them by adding new functions into the library. Because, however, the refactorings there are too many. They use some ideas from the other research to efficiently reduce this refactoring search space. And they also limit it to just a small functions that are being searched for, and they are able to limit this to search over about 1 million potential refactorings, potential suggestions of the new functions into the library. And then in the dream phase, it replaces the solution that was able to solve about 100, mixes it with the generator replayed programs. The generator, I think, is trained in the wake phase. I'm not 100% sure how exactly the generator looks. It's supposed to be some kind of sampling from programs. I'm not 100% sure. And why they do this generation, why they mix it with the real program, is because they want to be sample efficient. So this is like a data augmentation. And during the dream phase, they train the search function, the Q functions. So again, a couple of examples. So for this logo task, they have these tasks to solve, and they learn library functions like a semicircle, circle, spiral, Greek spiral, and so on. And once they learn these functions, they then further learn additional functions, this sort of this radial symmetry function. And by adding these functions into the library, it's able to produce more and more abstract solutions. So it's able to solve more and more problems. So this can be observed also from the dream phase, where on the picture here, D, it dreams sort of very simple logos just made up of simple lines randomly aligned. But in the further dreaming phase, once the library is much bigger, it can learn much more. It seems to be not suddenly more sensible because it can use the abstraction, so it's a bit more complex, and also it looks a bit more natural thanks to that, because we added this bias of the learned functions. So the results. So, for example, in REST processing, by training on 100 training tasks, the library created 20 routines, including filter, maximum of the list, and largest of the list. And using these, it was able to learn to sort the list. It's not efficient sort, it's some sort of insert sort, but still very interesting. In the text editing, they were trying to compare with some existing programming synthesis competition. Unfortunately, they sort of used some sort of auto-generated text editing style, so it's hard to evaluate how they really compare. But so it's not really, this benchmark is not really comparable between between this and the previous solution. At the same time, they seem to do well using the auto-generated examples. I don't know how they look. It really depends a lot, what kind of bias they can introduce here, such that they can outperform test set. Not sure, but what's interesting that they were able, with some sort of similar compute, be competitive in number of percentage of the solutions to the prior art. What's interesting that the others, when they were solving these problems, they used some handpicked libraries for the specific problems, where the DreamCoder instead created the library itself. But it's hard to tell if it's really better. Maybe to add why they explain their paper is better is that they of course mentioned that they build on some previous research. They build on robust fill and DeepCoder. DeepCoder is different in that it does not predict the probability of program. It predicts how the DSL primitives probability, what kind of DSL primitives are going to be in the program at least once. So this is different. They instead learn probability of the program distribution over the programs given the input outputs. DeepCoder and DreamCoder libraries have advantage in that those are modestly sized, generally sort of useful human interpretable routines. So that's the advantage. The DreamCoder lends a library which looks much more human-like than some sort of huge brute force genetic search. That seems to be the advantage. You can find out more in these two links at the end of the post. There's a video from the author, and then here's also a link to the paper, which also has supplemental information. And in the supplemental information, many of the details are covered, which are not present in the archive preprint as of today. All right, so that was the DreamCoder, which composed of this wake phase, with its neurally guided search, abstraction, where it does refactoring of its stored library, and dreaming, where it trains the search using generative model and replays. So I hope you got the gist of the paper. Thank you very much, and hope to learn more.